So like, so yeah, you know. Yeah,
Oh,
those
electrical, okay.
he's making a AC. See, that's it. To turn electricity into rotation.
Oh, so it's gonna be.
Yeah. But you could do it opposite.
Yeah.
I told you, I asked you.
Just for you. For you. No, I'm saying for you. Yeah, that's not, I thought it was gonna be. It's gonna be a positive. Yeah.
So then I was eating chocolate, like chocolate. So. Yeah. Yes. Yeah.
Yeah.
Yeah. Yes.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing? Hopefully everyone's not too sleepy after the daylight savings. I didn't even realize it was daylight savings until I woke up. It's like, oh my God, I slept in. But no, it was just that hour got pushed ahead. So okay. So first thing, obviously, you can see I did finish grading your midterms. I'm a little bit ahead of schedule on that. So I did bring them today, although I did tell everyone I'd bring it on Thursday, so I'll bring it back on Thursday as well. Though it seems like most people did. So you guys did great. You guys did fine. You guys did good on the exam. So the average was 35 out of 50. It seemed kind of when I was grading, kind of an issue that a lot of people kind of had was timing. So I just want to just kind of tell you guys that the way I typically grade exams. I look at the final result, of course, but what I'm looking more at is kind of how you kind of set up the problem, kind of your process in solving it. So I graded more of that, more so than the final result itself. And so I tried to be kind of as generous as I could with partial credit, and then the average ended up being 35 out of 50, which is basically historically same for every class that I've had so far. So this would be also a good time to kind of remind you the grading policies in the class. And so remember, we have 2 midterm exams. So the second midterm is going to take place after spring break. Remember, there's different weightings on the 2 midterms exams. So one of your midterm exams is going to be worth 30% of your grade. The other midterm exam is going to be worth 20% of the grade. And the way I choose is whichever midterm that you score higher in, I'm going to weight that one towards, I'm going to give that one a heavier weight towards your grade. So that one's going to be at 30%. So you did really well in this midterm exam. That's great. That's 30% of the points in this class kind of in the bank. And so, your next exam, there's a little bit less pressure on it. If you didn't do so well in this midterm exam, you have the next exam to really kind of make up for it. And next exam is worth 50% more than this exam. So in terms of scaling the grades or curving the grades, so I don't curve the individual exams or individual assignments. So remember what I do at the end of the semester, once all the grades are in for all of the exams, the homeworks, the final exam, what I'm going to do is I'm going to look at the overall class average. And if the overall class average is below my usual threshold for 3 weights, so my usual threshold for 3 weights is around 78, 79%. So let's say the overall class average was kind of same as a midterm, which is a 70%. What I'll then do is I'll add, about 8, 9 points to everyone's grade until the overall class average is at that threshold. And so, this is pretty much in line with this because, typically the exams are a little bit lower than that threshold, the homework's a little bit higher than the threshold. So everything kind of balances out to that kind of average. But, if there's some adjustment that needs to be done at the end, I'll do that kind of at the very end. I'm not going to curve the individual exams. Okay. So I brought the exams today, so I'll end class maybe about 5 minutes early today to give you a chance to pass them back out and you guys can look at them. And if I made any mistakes, and so if I made mistakes adding the points up, or if you don't understand kind of the why I took points off, definitely talk to me. I'm always happy to kind of chat with you and kind of go over that and adjust your grade if needed. Okay. All right, and so besides that, plan for today is to continue on with our lecture that we started on Tuesday. So last Tuesday, we kind of started on lecture notes on vector. It's basically just a review of vector algebra. Today, we're going to get into some of the vector calculus stuff. So going over things like the gradient, the divergence, the curl of these fields, and kind of giving them a little bit of physical intuition as well in terms of like how they're applied in an engineering context. Okay. All right, any questions before we get started on the exam or anything we covered last week? Okay, all right, so let's go ahead and get started. Okay, so topic for today is going to be what I call differential vector calculus. So, in other words, we're looking at calculus of functions of multiple variables, right? That's kind of what we started last time, where we talked about vector quantities, field quantities, which are basically functions of multiple variables at once. Okay. All right, so that was field quantities and vectors. And so, remember the kind of what we went over last time was we looked at a function, let's say it's a function of two variables, x and y, okay? So a function like this, we'd say is a scalar function because it has a single value f. It's just that f may depend on two or more variables, okay? So this function here basically assigns a single value. And so it assigns a scalar value to a pair of input variables, so to a pair of x and y variables. Right. So this is kind of rudimentarily kind of what we define as a field image. Okay. Because usually that x and y, for engineering applications, usually that x and y kind of refers to some location, some physical location in space. And so we say it's an x component or the y component. Okay. And of course, f is the value that we assign to that physical location. Okay. So some examples, right? Or one example, I guess, one example that's very common in mechanical engineering is this idea of a temperature field. So a temperature field is nothing more than just, just the temperature of a particular object, assigned to each kind of X, Y location in space. So let's say we have kind of a rectangular domain like this. Right? We have the axes, x-axis, y-axis, right? And so the temperature field, which we can denote as T of X and Y, right? Temperature is a scalar quantity. So it's, it's just, we're going to assign just a single value or single number to each point in space, right? That means for each location here, each location is going to have a temperature that's associated with it, that's defined by the function. So let's say this is maybe 100 degrees C, maybe this is 95 degrees C, 90 degrees C, 85. I don't know why I put these so close together. Okay. And so on and so forth, right? So each location can have a different temperature, and that's kind of what we described. Okay. So the first kind of operator that we're going to go over in this kind of area of differential vector calculus is this idea of a gradient. So the gradient of a scalar field is a derivative operation where we're going to compute the rate of change of the scalar field with regards to each of the independent variables. So for a field function here, that's a function of two variables. Our gradient is going to have two components, right? So if you have f of x and y, because remember, when you have a function of multiple variables here, you can take what's called their partial derivatives. So you can take a derivative in each of the independent variables, right? So you have partial f, partial x. This right here is a partial derivative in the x direction. Another way to kind of interpret this expression here is that it's the rate of change of f as with respect to x. Sometimes you'll, especially in this unit, you're going to see me use the acronym WRT. WRT stands for with respect to. And then we can make the same, a similar expression in terms of the other independent variable here, which is y. So we have partial f, partial y. So partial f, partial y, this is the partial derivative in the y direction. All right. So the gradient of a scalar function basically takes each of these partial derivatives and kind of puts them all together into one structure. Okay, so the way that we denote the gradient is we use this kind of upside down triangle symbol. And then we apply that upside down triangle to our function f. And if you were ever curious what that upside down triangle or what that symbol is called, this symbol is called a nabla. And so the gradient of a function, in other words, nabla f, is going to be each of the partial derivatives, but we put them into one single structure. Okay. So partial f partial x, comma, partial f partial y. Okay. Now this structure here is unique because, you know, these aren't just kind of a couple here, right? So this structure here specifically is actually a vector field. Right? And so we can actually express this in kind of IJK notation. In this case, it would be just IJ notation. And so the gradient of a scalar field will be partial f partial x multiplied by I hat plus partial f partial y multiplied by j hat. Okay. So partial f partial x, that's the x component of the gradient, and partial f partial y, that's the y component of the gradient. Okay. And so this kind of highlights one very important property of the gradient, in that it actually kind of takes your function and kind of steps it up a dimension. Okay. So you can see here that if we take the gradient of a scalar field, we end up with a vector field. Right. So another way that we can say this is that the dimensionality of the field actually goes up by one. Okay. So if we're going from scalar to vector, right? From the scalar value function to vector value function, that goes from a 1D structure to a 2D structure. And this same trend actually kind of applies too. So we're not going to do in this class just because it gets a little bit too intense on the details, but you can actually take the gradient of a vector field too. And so the gradient of a vector field actually gives you what's called a tensor field, tensor valued function, in which, you know, for every location, there's not just two or three components, there's a full matrix of things that are there. And that's actually quite common in engineering as well. So you're talking about, you know, shear stresses and fluid mechanics or solid mechanics. Normal stresses, typically you represent that in tensor. But we're not going to go there. We're just going to go from scalar field to vector field. Okay. Okay. So the gradient is actually used for quite a lot of things. And so we're going to spend actually the majority of today talking about the gradient. But, you know, we're going to do some examples on how to compute it first as well. But before we do that, any questions on this so far? Okay. All right, so let's look at an example really quick to see how we can compute this. Okay. By the way, what I've shown you up above there, that's the two-dimensional version of the gradient. You can also take gradients of three-dimensional functions as well. Okay, so functions with three independent variables. So, for instance, let's say we have a scalar field here. So we only have a single value, but let's say it's a function of three variables, x, y, and z. So let's say f of x, y, and z is equal to 2y cubed plus 4xz plus 3x. And so what we're going to do in this example is this: we're simply going to compute the gradient of this function. Okay. So in other words, we want to compute nabla f. All right, so to compute nabla f here, we're going to compute the partial derivatives in each of the directions. And so that's first order partial derivatives in x, y, and z. And we're going to put them all into the same vector field. Okay. So nabla f here is going to be partial f, partial x, partial f, partial y, partial f, partial z. Okay, so let's go ahead and compute all of the partial derivatives. So remember, when you're taking a partial derivative, you're only taking a derivative of that variable that you're taking the partial derivative of. All the other variables that are there are just merely treated as if they're constants. Okay. All right, so let's do partial f, partial x first. Okay, so we're going to take our function f and then take the partial derivative with respect to x. Okay, so basically everything with an x, we're going to take the derivative of that. Okay, so that means we're going to have partial x of our function f here, which is 2y cubed plus 4xz plus 3x. Okay. All right, so everything that's not x here, so that includes all the actual constants, so 2, 4, and 3, but also all the other variables here, y and z are also going to be treated as constants. Okay, so when we take this derivative, the first term that we come up to is 2y cubed, right? So when we take the derivative of this with respect to x, remember, we're treating y as if it were a constant. So taking the derivative of this with respect to x, this just goes to 0. The next term that we have in this expression is a 4xz, right? So remember, 4 and z, we're just going to treat them as constants. And so we're just going to take the derivative of x. And so we are going to get something there. Right? And so that's just going to be 4z. Okay. Right. And so since those are constants, those are just kind of get carried along. And since the x is there, we do actually take the derivative. And same thing for the 3x here. And so the 3x, that one's probably simplest just because there's only just one, it's just a single variable part here. And so taking the derivative of 3x just gives us 3. Okay. And so that's our first partial derivative, 4z plus 3. Okay, so let's go ahead and continue. So let's take the partial derivative with respect to y. So we have partial y of 2y cubed plus 4xz plus 3x. Okay. Once again, we're going to look at all the terms with y and then treat everything else as a constant. So since the two second terms here, neither of them have y. And so when we take the derivative with respect to y, both of those terms go to 0. And so the only term we're taking the derivative of is the first term, which is 2y cubed. And so we take the derivative with respect to y, we end up with 6y squared. All right, and then finally, really quickly, let's take the derivative with respect to z. We have partial z of 2y cubed plus 4xz plus 3x. Okay. We're going to cross out everything that's not a function of z. So 2y cubed and 3x, neither of those have z. So we're going to cross those out. And the middle term, we take the derivative with respect to z. We end up with just 4x. Okay, so let's put this all together. Let's put it all into the same vector field. And what we get is 4z plus 3 comma 6y squared comma 4x. And this right here is our gradient. All right, any questions on this example here? How we got each of those components? Okay, good. All right, so the gradient's actually really cool, and so it actually has a lot of really interesting uses here. First of all, I think it's really interesting we actually get a vector field from this. And that vector or the direction of that vector can tell us something that's really kind of interesting. Okay, so we're going to go through, I would say, two of the most common uses for the gradient. So the first one we're going to go over is something called the directional derivative. And the other thing that we're going to do is something called the direction of maximum increase or the direction of maximum decrease. Okay, so let's go through each of these kind of applications because they both kind of have a lot of applications within ingredients. Okay, so let's go over the directional derivative first. Okay. So when you have a multivariable function or a multivariable scalar function, oftentimes you want to find out how that function, how it's going to be changing in each of the directions. And so I'm using the word direction here just because typically X, Y, and Z, those are kind of physical directions, but you can use those X, Y, Z or variables to represent other things as well. Okay. So we already know how to compute this for each of the cardinal directions. So X direction, Y direction, Z direction, that's already covered for us just because we can just take the partial derivative in that direction. You have partial F, partial X, partial F, partial Y, partial F, partial Z. Okay. So if you're interested in just the rate of change of the function in each of those directions, we're in luck because we've already kind of we parameterized our problem in terms of those three directions, and so taking the partial derivative straight up, that gives you the rate of change in X direction, the rate of change in the Y direction, and the rate of change in the Z direction. Okay, but what if you want to compute the rate of change in a direction that's not X, Y, or Z? So what if you wanted to compute the rate of change in some diagonal direction, right? And so let's go back to our temperature field from before, right? And so our temperature field we know is given by T of X and Y. Okay. And so if we want to find out how the temperature field is changing in the X direction, we just compute partial T partial X. Okay. So this direction we have partial T partial X. Right, that's going to tell us how our temperature field is changing in the horizontal direction. If we want to see how it's changing in the vertical direction, we have partial T partial Y. Okay. But what if we want to find out the direction of how, we want to find out how the temperature field is changing if we walk into a diagonal direction like this? And so we can't just use our partial derivatives for this because we haven't parameterized the problem in that direction. Okay. All right, so luckily for us, there is an easy way to do this, and it involves using the gradients, okay? And that is basically what's called the directional derivative. Okay. So the directional derivative basically lets you take the derivative in any direction. And the way to do that is to take a dot product between a vector and the gradient. And so if you take the dot product between a vector and the gradient of a function, that will give you the rate of change of that function in the direction of that first vector. All right, so the way to do this and the way it's usually denoted is we give it a capital D underscore A of F, okay? Right? So the way this is that you take A, right? A is some vector, a vector which denotes your direction. And you take the dot product between that and the gradient of F. Where this A here denotes a direction. So normally when you use this equation, that A vector is assumed to be of magnitude 1, just so there's no biasing that occurs when you take this dot product. And so if you want to make sure that there's no biasing that occurs, typically what you do is you normalize this vector. And so you basically take this vector and you divide it by the magnitude of that vector. And so that process there, you divide by the magnitude, you basically get a vector of magnitude 1. You don't bias any particular direction. So, it's literally just the rate of change in that direction. Okay. Any questions on this before we do a quick example? Okay. All right, so let's do a quick example of this just so that you can see how it works in practice. Okay, so let's say we have a three-dimensional function here, and we'll keep it simple. So we have f of x, y, and z. We'll say this is 2x squared plus 3y squared plus z squared. Okay. So that's our scalar function, that's our f. And let's say that we want to take the directional derivative of this function in the following direction. So our direction here is going to be 1, 0, -2. Okay. So that a vector there points in a particular direction in three-dimensional space, and so it's 1 unit in the x direction and -2 in the z direction. So it's kind of a diagonal direction with a little bit more bias in the z direction. And so we want to find out how our function changes in that direction there. Okay. So we're basically just going to apply that formula above there. So first thing, let's compute the gradient. So our gradient here, we have gradient of f, right? So we're going to take the three partial derivatives here. So partial derivative with respect to x, partial derivative with respect to y, and with respect to z. Okay. So this one's very simple. Everything is kind of segregated out. So our gradient here is 4x, 6y, and 2z. Okay. All right, next thing we're going to do is we're going to take our a vector and dot product with f. Okay. So we have our a vector here, which is 1, 0, -2. We're dot product that with our gradient, which is 4x, 6y, and 2z. And so this gives us 4x minus 4z. Okay. But we have to normalize this. And so we have to make sure that our direction vector has magnitude 1. So let's go ahead and divide this by the magnitude of a. Okay. And so on the side right here, let's compute magnitude of a. So magnitude of a, we're just going to use our Pythagorean theorem or distance formula, kind of whatever kind of feels most comfortable to you. Okay. So we're going to take the magnitude of the vector a, and so that's going to be 1 squared plus 0 squared plus -2 squared. Okay. That's going to give us √5. And so the directional derivative of this is going to be 1 over √5 times 4x minus 4z. All right, any questions on this example here? Okay, good. All right, so one thing you should notice here, and one thing that you may have noticed, in our last two examples, is that our derivatives here are non-constant. So the value of our derivatives actually change when you get to a certain location in the field. So this is not unique to multivariable functions. In fact, this is true in 1D functions as well, right? So depending on where you are, the rate of change is going to, well, change, right? And so if you would think of a simple quadratic function, the slope is kind of ever increasing as you get further and further away from the origin, okay? Same thing with this directional derivative here, right? So this directional derivative, you can see, depends on x and z. And so what you can do, if you want to find out the exact rate of change at a particular location, you can evaluate this at those locations. So one common question that you may be asked is, what is the value of the directional derivative at a particular location, x, y, z? So let's say we want to evaluate this at location 2, 1, 3. And so to evaluate the directional derivative, you're just going to plug this into our expression up above there. Okay, so you're going to plug in x is equal to 2, y is equal to 1, and z is equal to 3. Now, of course, our directional derivative here doesn't have any y, and so we're not going to plug in anything for that. But we can plug in for x, and we can plug in for z. Okay. All right, so we do that, we get 1 over root 5 multiplied by 4 times 2 minus 4 times 3. Okay. Of course, we get kind of a weird number here because of the radical. And so what we get from this is minus 1.78. So that right there is the value of the directional derivative at that location 2, 1. All right. Any questions on this example here? Yeah.
The 2, 1, and 3, do you get it from the equation above?
That's just a random point.
Oh.
Right? Yeah. Yeah, so you can evaluate that directional derivative at any point. So the 2, 1, 3 is just, I just pulled that out of from my place. Okay. All right, so that's the directional derivative. Very useful. One use that that comes to mind is that if you're doing structural mechanics, and you want to find kind of the direction of kind of maximum stress increase, and so you want to find out which direction along your part is the stress increasing the most. That's usually something that's valuable to know, because then you can choose to kind of reinforce your structure in that direction, because the stress or the strain is increasing in that direction. And so being able to take derivatives in kind of an oblique direction is very valuable for engineering practice. Another very interesting application for the gradient is the direction of maximum increase. Okay. Now, there's a lot of engineering applications for this as well, because when you have kind of a complex field of variables, you want to oftentimes the direction in which that variable is increasing the most or decreasing the most, that's going to tell you something really important about that field. Okay. All right. So remember, when you take the gradient of a scalar field, you end up with a vector, right? And that vector has a direction to it. Oops. Great. Okay. And so the direction of the vectors in that gradient field actually tells you the direction of maximum increase, or the direction where, if you were to walk from that location in that direction, your function is going to be increasing the most in that direction. Okay, so it's actually quite interesting. If anything, just to graph it out. Okay, so remember kind of the definition of a vector field that we went over last time. So for a vector field, for every location x, y in your domain, you're going to have a vector valued quantity at that location. So that means, for every location here, right, the gradient is actually going to have a particular direction that is going to be pointing in. Now, they don't have to all be the same direction. In fact, let me kind of change this up a little bit. So each arrow here represents the gradient of that function at that location. Okay. And so remember, what the gradient represents is that if you were to go from that location in that direction, that's the direction where your function is going to be increasing the most. And of course, this changes kind of location to location, just like, the directional derivative or just any scalar vector quantity. Okay. So oftentimes, if you want to, always kind of travel in the direction of maximum increase, your path may change, right? And that direction of that path is given to you by the gradient itself. All right. So like I mentioned, this has a lot of applications in engineering. In fact, a lot of kind of central theory or central kind of concepts and things like heat transfer, fluid mechanics are based around this theory. Okay. Okay. So I know maybe a few of you are taking heat transfer right now. Some of you are taking heat transfer from me right now. But I'm going to teach you heat transfer in 10 seconds. So the way heat transfer basically works is that energy or thermal energy always moves from high temperature to low temperature. So that's heat transfer or EGME 407 in a nutshell, right? And so if you always kind of remember this, then you're pretty good. So you're better than most people who don't understand heat transfer. Okay. So in a one-dimensional case, this makes sense, right? And so if you have, if you can either go forward or back, you're always going to go into the direction of what we say the decreasing temperature gradient, and you're going from high to low. okay? But let's say that you're in kind of a complex geometrical, two-dimensional, three-dimensional space, right? Sometimes it's not as clear kind of which direction is hot and which direction is cold. So let's look at that. So let's look at kind of a situation like this. Okay. Right. And let's say that, let's define the temperatures at each of the corners. So let's say that the top left corner, this is going to be 100 degrees C. Okay, fairly hot. The bottom left corner, let's say that it's slightly cooler. Let's say that's 80 degrees C. Okay. And on the right, let's say the top right corner, that's going to be, we'll say that's 80 degrees C as well. Okay. And then the bottom right corner, that's going to be our one cool corner. So let's say that the bottom right corner is going to be 60 degrees C. Okay. Basically, we know the temperature at 4 fixed locations in our domain. And we're going to assume that the temperature kind of varies smoothly in between each of these locations here. So there's no kind of weird surprises here. Okay. Okay. So based on the statement above, which states that energy flows from high temperature to low temperature, generally what you can expect from this situation is that most of the energy is going to kind of funnel into that bottom right corner, right? And so if we look at the path of heat, actually let me use I'll use pink for this. Okay. Generally, heat is going to go kind of in this direction here, right? So it's all going to kind of funnel into that corner because that's kind of the coolest location on the plate, right? So that's generally what you expect, for a relatively simple heat transfer scenario like this. Okay. But let's say we didn't know the temperatures at the corners, right? You can still get the same kind of heat flow field by simply taking the gradient of the temperature field. Okay? Well, I guess in particular here, we're going to look at the negative gradient, right? And so the direction of gradient tells you the direction of maximum increase. In this case, we actually want the direction of maximum decrease. And so we're going to take the minus gradient. Okay. And so we take the minus gradient of the temperature field to the function of x and y. Okay. Right. And so this is going to tell you the direction of heat flow. Okay, and there's lots of kind of similar applications like this as well. Okay, another one, which I'll only just kind of talk about just because of time, but another one that's in the notes is say that you are hiking, and so if you've ever hiked kind of a region with kind of a lot of topological differences, you'll probably see a topology map at some point, which tells you kind of the relative height of different parts of the region. You can take the gradient of that height chart. And so the height is nothing more than just a multivariable function, right? And so if you take the gradient of that height chart, that'll tell you the direction of maximum descent or maximum ascent. And so if you want to kind of trot out a hiking path, you want to generally avoid areas where the descent is very high, because otherwise you're going to tire yourself out, climbing up a vertical wall. And so generally you want to path around it. So you want to find areas where the gradient is not so extreme. Okay. And by consequence, you want to avoid those areas as well, because if you fall off the trail from a location where the gradient is very high, you're going to have a very painful stumble down the mountain because you have a very steep descent from. Okay. Any questions on this? Okay. All right. So another thing I want to talk about, this may be the last thing that we have time for. We'll probably go over curl next time. Is the divergence of a vector field. Okay. So the gradient is the main operation that we're going to take on a scalar field. The next two operations that we're going to talk about, both the divergence and the curl, these are only operations you can do on vector fields. Okay. Okay, so the first one we're going to go over is called the divergence. Okay. And so the divergence is basically an operator that takes us from a vector field to a scalar field. So you can kind of think of it as almost like the opposite of a gradient. And so in contrast, for the gradient, we say that we increase the dimensionality by 1. By going from a vector field down to a scalar field, we're going to reduce the dimensionality by 1. Okay. And so the way that we're going to achieve this, we're going to make use of our nabla operator again, but we're going to use it in a slightly different way. Okay. Okay. So for this one, this needs a little bit more documentation. So let's say that we have a certain vector field. Okay. So we'll say our vector field is given by V. Okay. And remember, the way a vector field works, just like the gradient, is that our vector field has separate components. We'll say that this vector field has 3 components, and each component of that vector field can change with respect to X, Y, and Z. Okay. So if our vector field here has 3 components, we'll call Vx. Vx is a function of X, Y, and Z. Okay. We have Vy, so that's our second component. So Vy can be a function of X, Y, and Z. Okay. And we have Vz, which is also a function of X, Y, and Z. Okay. So another way you can think of a vector field is that a vector field is just a combination of 3 scalar fields, just all lumped together. Okay, so the divergence of this vector field. So the way we denote that is we take the nabla. It's like we're taking the nabla dot product with the vector field V. Okay. It's given by the following expression. So we have partial Vx, partial X, plus partial Vy, partial Y, plus partial Vz, partial Z. So this right here is the divergence of vector field V. Okay. So basically, you're going to take the partial derivatives of each component of the vector field with its matching kind of variable, right? And then you're going to add them together, right? So you're going to take the partial derivative of the X component with respect to X, partial derivative of the Y component with respect to Y, partial derivative of the Z component with respect to Z, You add them all up, that's going to be your divergence. Okay. Okay, so let's do a quick example, just kind of show you how this works. Okay, so let's say that we have a certain vector field. So we'll say V is equal to 3xz, comma 2xy, comma y, negative yz squared. Okay. So you can see our vector field has 3 components, and each component is a function of x, y, and z. Okay. So let's find the divergence of this vector field. Okay. So to find the divergence, we're just going to take the partial derivatives of each of the components with the matching variable. Okay. And so the divergence nabla dot v is equal to partial x of 3xz plus partial y of 2xy plus partial z of minus yz squared. All right, so let's go ahead and evaluate these 3 partial derivatives here. So we have partial x of 3xz. That's going to be 3z. Okay. We have partial y of 2xy. That's going to give us 2x. And then we have partial z of minus yz squared. So that's going to be a minus 2yz. Okay. And that's going to be our divergence right there. Notice how it's a single expression, it's a single scalar, because remember the divergence takes a vector field and transforms it into a scalar quantity. All right, any questions on the divergence here? Okay. All right, so taking the divergence, it's once you kind of understand partial derivatives, you understand scalar vector fields, it's not too complicated. It's just partial derivatives. But just like the gradient, I'm going to spend kind of most of the time talking about applications. Okay, so where is the divergence used? So the divergence is a very important quantity for fluid mechanics, actually. So if you took 333 last semester, probably you've kind of seen the divergence already. If you're taking fluid mechanics next year, you'll definitely see this. If you're not in mechanical engineering, you're not taking fluid mechanics at all, don't worry. This is just an example to kind of show you what it's useful for. But the divergence is used for other areas as well. It's just fluids is kind of what I'm kind of most familiar with, just because my training is a mechanical engineer. Okay. So in fluid mechanics, we often use the divergence to express a very important property of fluids, which is conservation of mass. So basically what we have in fluid mechanics is that if V, okay, where V here represents your velocity field, okay, So it tells you the direction and magnitude of the velocity at each location in space. Okay, that's something typical that we solve for fluid mechanics, usually through Navier-Stokes, something like that. Okay. So if you take the divergence of the velocity field, okay. So basically take our nabla, we dot product with our velocity v. Okay. What you should get is that the divergence for any velocity that is, or any velocity field that is mass conserving. So, the fields where, mass is not created or destroyed, the divergence should equal 0. And so, when you're doing kind of fluid mechanics problems, you're doing Navier-Stokes type problems, this is kind of one of the first things that that you should check, is to make sure that, the divergence is 0. Okay. This particular equation right here has a special name just because it has such a, unique kind of, importance to fluids. We often call this the continuity equation. All right, so physically, in this case, if the vector field V represents a velocity field, what the divergence kind of shows you is how much that field is kind of stretching out or compressing. And so for a proper kind of mass conserving fluid flow, if your fluid is going to conserve mass, you're not going to be able to stretch out any of the fluid particles, because they're basically incompressible. That's basically what we say. Okay. Unless, of course, you have a compressible flow. And so if you have kind of a gas that's moving at a very high speed or very high temperature, that's a little bit different than the density of the fluid can be a little bit different. It's a little bit more kind of fluid, I guess you can say. And so in those cases, those are situations where your continuity equation could be violated for compressible flows. But for the vast majority of fluids, you should have the divergence equal 0, just because it's not possible to take, a fluid molecule and kind of stretch it out any more than it can, because it's, it has a fixed amount of mass. Okay. Now there is some theory that that does give some exception to this. And so one potential field that violates this is a theory called potential theory. Oops, I should be consistent. Let me use V here. Okay. So potential flow theory is something that's often used in aerodynamics. And so if you go to aerospace engineering, potential flow theory is something you'll use a lot. It technically violates the laws of conservation of mass. But when you're talking about aerodynamics, you're often talking about regions with very large amount of fluids. You're talking about the air around an airplane, and so having a theory like this can be very convenient. So, and so some just to give you kind of a preview of that, if you have regions where the divergence is greater than 0, we call this a source. Okay. So those are regions where fluid is kind of being added to your system. Okay. And so you have we say it's a source or a source of kind of fluid mass, right? Right. If you have the divergence less than 0 in certain regions, this is a sink. Okay. And so in other words, those are regions where you're going to have fluid that's kind of being lost. Okay. Right. So the way potential theory works, just to kind of give you a quick overview, just because we're just about out of time, it's okay to have, certain small regions where you violate continuity. And it's kind of very based on this idea of the divergence. Overall, you shouldn't violate continuity, but in certain small regions, it's okay to do so just for the sake of approximation. And that often leads to a lot of simplifications that you use to do things like design airfoils, design kind of the fuselage of an airplane. Okay. All right, any questions on this before we wrap it up for today and we pass back the exams? Okay, all right, so when we come back on Thursday, we'll go over the curl, and then we'll move on to integral calculus. Okay, so I have your exams up here, so feel free to come up and grab them. I put them in a bag so they wouldn't get wet. But yeah, so they're not in any particular order, so you just kind of come up and grab them. And if you're on Zoom, I'll bring the exams again on Thursday, so you can come pick it up on Thursday. Yeah.
I'm watching your videos about the movies equation.
Yeah.
And they explain it using like a pipe analogy.
Mhm.
And I was wondering, like, could that analogy be like used to describe charge in a wire?
Yeah, actually you can. So actually that whole idea of using pressure differences to compute load, you can do the same thing for current and voltage as well. So difference in voltage will basically drive current. And so basically, yeah, same, except in circuits, you don't have what's called, there's no concept like viscosity or anything like that. So it's a little bit limited, but the same idea kind of works as well.
Yeah, because they explain it like water on one end pushes water on the other.
Yeah.
And I remember because electrons on one side, they don't flow through these.
Yeah.
Yes. I think I'm gonna try to take a word that uses a fluid.
Yeah.
I'm electrical and they don't offer that.
Oh, okay.
Thank you.
Yeah. I'll post the solutions, yeah, later. I brought the exam today, but I left the solutions at my home, so. That was great. The reason I graded them quickly because my wife was sick over the weekend, and so I had nothing to do except grade them.
Professor, I have a question. How do you find the infinity? This was a shot that covered.
Yeah, so the infinity, that's basically, you kind of have to go over the description on this one. So the infinity is kind of when the test kind of wax it. Okay, so that's an impulse function.
Right.
So the impulse, you don't actually put the value there, you just put delta.
Oh, okay,
Yeah.
okay.
Yeah.
Sweet.
So I saw that you got it. Just figured it out there, but crossed off the page.
Okay, no worries. I'm in class with Jerry next, so I'm gonna take his exam.
Sure. Yeah.